Okay, so let's now go through and start deriving what a Lorentz transformation is going to be. Okay, so just to remind you, a Lorentz transformation is going to be a coordinate transformation between two reference frames. So if we have some reference frame x mu, remember this is just a for tuple specifying the coordinates in the x frame, we're going to then have some kind of transformation, the Lorentz transformation, that's going to take us into our new frame, y, and we're now going to assume that this is going to be a linear transformation, i.e. we can express the new coordinates as some linear combination of our old coordinates. So this lambda, the Lorentz transformation, is just going to be a matrix of coefficients, and then whatever those coefficients are, they're simply just going to linearly multiply each of our coordinates, and that's how we express the new coordinates. So just really quickly, this is a linear transformation. An example of a non-linear transformation would be, say, switching from Cartesian to polar coordinates, because in, say, polar coordinates we have to express the Cartesian coordinate as now something which is not a linear combination of the old coordinates. This is r multiplied by the cosine of theta. There's no way we can express this as some kind of matrix times the coordinates to give us our new coordinates. There's just no way that you can linearly produce something like this. This would be an example of a non-linear coordinate transformation. So that's not what we're doing. And in fact, starting to consider non-linear transformations is already going to take us into general relativity. So we're just sticking with the linear case for now, which basically means that we can write, I'll just write out in full. If I start representing the coordinates as just a column vector, so let's say the y mu might have coordinates ct hat, y1, y2, and so on. This is now just going to be some matrix of coefficients multiplied by the old coordinates x. So now it's going to be up to us to determine what possible matrices can go here, and to do this we're going to use the isometry requirement, which I mentioned in the previous video. Okay, so we're looking at our linear transformation, and now we're going to try and derive essentially what possible matrices we can write down here. Or rather, we're now going to use the isometry requirement to constrain the possible matrices that we could write. So the isometry requirement basically states that the metric is invariant regardless of the coordinates. So we're always going to have the metric components being the Minkowski metric. The metric components don't change. Remember, in general we would have had to write down some other set of components, but now we're imposing the requirement that the metric components don't change. Okay, so this is what we have to work with. We have our isometry requirement, and we have the form of our transformation. So now let's just simply start plugging a few things in. We know that the new coordinates, this is how we express them in terms of the old coordinates. So why don't we just substitute in for y in this expression. So I'll just rewrite the left-hand side quickly. And now our metric components are the same, but now we have to have dy, which is going to be d for this whole object, and then another copy of another dy. So I need, now I'm getting in trouble with my indices. So to keep my indices consistent, I need, so I'm trying to end up with a mu upper, and then to avoid introducing a duplicate index, I need a new dummy index to sum the x against. And then similarly, I want to end up with a new upper here, so I need a new dummy over here. So all I've done is just simply substitute in this expression over here, and now what we have to do is just compare these two expressions. Well, this d, the exterior derivative operator, it's basically not going to see this lambda matrix because this lambda matrix is just some set of coefficients. It doesn't depend on the coordinates at all. So the exterior derivative isn't going to have anything to do with the lambda. So we can just pull the lambdas out and we find the following expression. Okay, now we have to compare these two expressions just to avoid any confusion which might arise with the naming of the indices. I'm just going to relabel indices on this expression. Remember, whenever we have a fully summed index, we can just relabel it to whatever we want. And so I can just now relabel, just rewrite the left-hand side. I haven't changed anything, I've just relabeled mu to sigma and nu to rho. Everything's the same. I'm just doing this so that I can match up my indice names effectively. But now we can look at this expression and we realise, okay, well we just have our dx's, we can chop those off, and we're simply going to be left with this expression, which we'll just rewrite. Okay, so first of all, just checking all of our indices match up. Sigma and rho are the only three indices we have. And here we've got fully summed mu and nu, and we're just left with a sigma and a rho. So this makes sense, at least index-wise. But now what this is really saying is that the metric is, well, this is kind of like a transformation law now for our metric components, but we should see essentially now this Lorentz transformation is going to have to do nothing to our metric components. It's going to have to leave them invariant. And so just by requiring the isometry of the metric, that the components are the same regardless of the frame, we've now derived the following expression, which is going to be incredibly useful. Going to be incredibly useful in constraining what these components can be. Okay, so far this expression isn't really telling us too much. Essentially it's just restating or making it explicit that this lambda is a coordinate transformation, because if you just now forget about lambda and just instead substitute here a Jacobi matrix, this all works out exactly the same as if this was any arbitrary transformation. And then you can essentially just realise now our Jacobi matrix is the Lorentz transformation, but we just have now the additional requirement that our metric components are the same. And so we can now add this expression to our list of useful expressions. Okay, so we've got somewhere now, we've realised the Lorentz transformation. Well, first of all, we've seen exactly its character as a coordinate transformation, and now we're going to further constrain its values by examining this expression in a bit more detail. So we need to realise these etas are essentially just the same matrix of numbers, and we can now use that to constrain particular properties of this lambda matrix. So let's just first of all consider taking the determinant of this expression. Just remembering we can just now kind of effectively view this as being a product of matrices. So let's take the determinant of the left-hand side, we're going to have now the determinant of these three matrices, and now just a general rule for taking determinants. The determinant of products of matrices is given by the products of their determinants. So we're going to have now the product of 2. So we're going to have the determinant of eta, and then now the determinant of lambda squared, because we have 2 lambdas here. And so now we can just simply cancel the determinant of eta to find that the determinant of the Lorentz transformation squared has to be equal to 1, or that the determinant of the Lorentz transformation has to be plus or minus 1. So that's another key property which we've now discovered, essentially without doing any explicit, or we haven't derived or shown any explicit form of this lambda, but just simply by imposing the isometry requirement, we've already come up with a fairly now strict bound on what these lambda matrices can be. They have to have a determinant of plus or minus 1. And so the fact that this is a plus or minus here, we're going to come back to slightly later on, but for now I just want to kind of note that whether it's plus or minus doesn't really make too much of a difference. It just kind of corresponds to reversing the direction of time. But really for the sake of, or for our case, it's going to suffice just to simply consider the case where we have the determinant plus 1. And so we're going to take this to be our requirement, or now another requirement that any lambda matrix has to have a determinant of plus 1. Okay, so now let's revisit this expression. Remember I briefly mentioned how we could have arrived at this just by considering the tensor transformation law, realizing this lambda is our Jacobi matrix of transformations. So if I just rewrite this expression now using the Jacobi matrix language, or rather the coordinate transformation language, if you remember we defined, if we had some coordinate transformation x to y, now for vectors we had that the Jacobi matrix was given by this expression, but for one forms or dual vectors we had to use the inverse, and so one forms transform with an inverse Jacobi matrix. So if I now make the identification that this lambda transformation is going to be our inverse Jacobi matrix, just simply write down the following formula. So remembering this is the form of our coordinate transformation. If I now express each coordinate transformation, all I've done here is simply rewrite this Lorentz transformation expression using the coordinate transformation language, or just the coordinate transformation law for a 0,2 tensor. So this here is our lambda. Let's now see what we can do with this expression. So if we just simply take now a partial derivative of this whole expression with respect to x. So take the partial derivative. This is just a constant matrix. Remember, eta is just minus plus plus plus, nothing that depends on the coordinates. So if I take a partial derivative, now I'm going to use my shorthand notation. So this partial subscript lambda is just shorthand for dx. Taking a partial derivative, just have to introduce a new index lambda. So this partial derivative here is going to be equal to 0 because the eta is just a constant matrix. But now what happens when we take partial derivative of this whole expression? Well, first of all we're going to have to use the product rule on this product here, but essentially, because this is just another copy of the same object, just with different labels, we can just say that the product rule is going to give us 2 times the partial derivative of one of these things. So when I take this partial derivative with respect to x lambda, what we're going to get is we're going to get a second derivative, so a d squared and then just our first expression. Okay, so all I did was just take another partial derivative of this expression. Left hand side gives me 0, the right hand side, using the product rule, just gives me 2 copies of the derivative of one of these things, and because these are already derivatives with respect to x, taking another partial derivative just gives us the second partial derivative. So now let me just rewrite this. Okay, just rewrote what I had before, but now because we know this has to be non-zero, essentially we can arrive at the following. And now again, because we know this has to be non-zero, because it already is one of our Lorentz transformations, we can arrive even further at the following, which now is simply saying, well, if we remember what this expression originally was, we were taking a partial derivative of now what we had originally, which was the Lorentz transformation. And so this can be just written as mu sigma, and so we arrive at now our final condition that the partial derivatives of these Lorentz transformations are 0, which we can now realise is just effectively being a restatement of our linearity assumption, because if these lambdas in any way depended on the coordinates, these derivatives would be non-zero. And so requiring that they are independent of the coordinates is just another way of stating that the transformation is linear. Right now, our final condition that the partial derivative of any lambda matrix is always 0, which is just another way of stating that the lambda matrix is a linear transformation. Okay, so simply just by making a slight assumption and then imposing the isometry requirement, we've now been able to derive 3 incredibly important formulae for Lorentz transformations, and we're going to now be able to use these properties to fully determine what the possible Lorentz transformations can be. And now just to go over what these conditions are saying, essentially, well, we've already said this one is just a restatement that the lambda has to be a linear transformation, i.e. the transformation in no way depends on the coordinates. And now this requirement is basically just stating that the Lorentz transformation is a coordinate transformation because it's going to transform the metric components in this way. But now what this requirement is saying is that the coordinate transformation isn't going to do anything to your components because they have to be the same before and after the transformation. And then this condition, essentially just saying that the determinant of the Lorentz transformation has to be +1 or -1. We're going to see shortly coming up is going to determine what possible now group that these transformations belong to. We're going to see that this is now just a generic property that comes from the fact that these Lorentz transformations are elements of a Lie group, which is going to be a special orthogonal group. And so, of course, any special orthogonal group element has to have a determinant of +1. So we can see that coming up, but for now, just want to remind you we've just come up or derived these conditions purely from the requirement that the metric has to be invariant under coordinate transformations, or that the coordinate transformations represent an isometry of the metric. They don't change the metric. The components are always minus plus 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 regardless of what coordinate system you use to write down the metric.